In the part B for Lab 3, we need to make a few changes, very minor changes comparing to the part A in Lab 3. So first of all, we need to replace the capacitor in the circuit with an inductor. So before that, let's turn off the output for the function generator for a while. So let's replace the capacitor. With the inductor. So now I made a change on the breadboard. So now the inductor is in series with the resistor. And we're going to use the function generator supplier input across both the inductor and the resistor. The second channel of the oscilloscope will monitor the input of the circuit, which is the output of the function generator. For the first channel of the oscilloscope, will be still monitoring the voltage across the resistor. So exactly same as the part A, except for that we replaced the capacitor with an inductor. So we need to make one more change on the function generator. We wanted the frequency to be 10,000 Hz instead of 100 Hz. So let's press the frequency button. So then we put 10,000 Hz, 10,000 Hz. So now it's 10,000 Hz and still 20 volts peak to peak. So now let's turn on the output button. So now output. So once we have the output, so we will have the signal on the function generator. What happened here on the function generator? Because the scale is set for the horizontal axis doesn't match for the frequency. Initially it's 100, last part A initially was 100 Hz. So now it's 10,000 Hz, it's 100 times more. So we need to adjust accordingly. It's one direction. So now we need to make it to be 50 microseconds for the horizontal scale. 50 microseconds per division. So let's tune a little bit more. Just get a couple of waves here. Just get a couple of periods here. So because as long as we have one period, we can do more, do all the analysis, right? So we're going to repeat the same procedure. We're going to tune the frequency on the function generator in order to get the yellow voltage, which is the voltage across the resistor, to be half of the input voltage. The input voltage of the green curve is 20 volts. So now the VPP of the yellow curve is 3.4 volts. We need to make it to be 10 volts. So let's try to tune the frequency. Let's see which direction it will increase the voltage across the resistor. So we need to decrease the frequency. So we got it on the first try. So if you initially tried to increase the frequency, you will see the voltage is decreasing. So we did our first try and got there. So in decreasing the frequency, the voltage will increase, right? So let's increase a few periods here. So now it's 5.4 watts. We need to make a 10 watts peak to peak. So now it's 9.5, which is pretty close. So now let's increase a little bit slowly. So now it's 3000 Hertz. $9.7 watts. $9.9. So now we have 10 watts. It's 2.7 kilohertz. So let's take a closer look here. So now it's 2.7 kilohertz. Remember, initially we set it at 10 kilohertz. So now it's down to 2.7 kilohertz. 2.7 here, in order to make the voltage across the resistor to be half of the input voltage. 10 watts out of 20 watts of input. So now let's take a closer look at the screen of the oscilloscope. So I try to maximize both curves to occupy as much as we can on the oscilloscope screen. So they have the same magnitude on the screen, but they do not have the same value because they have different scale on the y-axis. For the yellow curve, the voltage across the resistor. So the scale is 1.32 watts per vertical division. And for the green curve is 2.6 watts per vertical each division. So the green curve peak to peak is 20 watts, 19.9 watts. And for the yellow curve, peak to peak is 10.2 watts. And the horizontal axis, the horizontal scale is 100 microsecond per division. So in the next step, we're going to output the data from the oscilloscope to the MATLAB.